Hello everyone. In this session we'll discuss a question on expected value and variance. Let's move to the topic expected value and variance. So this expected value is expected value or maybe average value or mean in the sense mu is the weighted average of the possible values that x can take. So it's like if we have 5 different values that x can take, it's not like we can add all the values and divide it by 5. It is only possible when they all have the same equal probability as 1 by 5. If they have different probabilities of p of x1, p of x2, p of x3 like that, then we'll have to multiply the values with their average and then we can sum up it. Right? So this mean can be defined as, it is also given as E of x, can be given as summation of xi f of xi for all values of I for discrete random variable. Otherwise this is integral from minus infinity to infinity x f of x dx for continuous random variable. So either we'll sum up x fx or we'll integrate x fx. Now there are certain transformations which are also possible here, like if for x we have mean equal to mu, then for a times of x the mean is going to be a times of mu, and for the random variable a x plus b the mean is going to be a mu plus b. Right? If the mean for x is mu, a times of x, and that is scalar multiplication, will give the scalar multiplication of the mean. And if it is ax plus b, the mean is going to be a times of mu plus b. Also, if we have to find the weighted average of some function, let's say e of g of x is the function of x, then this is going to be sum of g of xj f of xj for all the j if it is discrete, or it will be integration minus infinity to infinity g of xj f of xj dx if it is continuous. So for any function we can find the weighted average for any function, like instead of x fx we can write g of x fx. And also if we have to find expected value of, let's say, a times of g of x plus b times of f of x, or instead of f of x let's write hx h of x then this can be written as a times of expected value of g of x plus b times of e of h of x, right? So this follows the property of linearity. Now there is kth moment of x, and this is given by e of x to the power of k, that is summation of xj f of xj and x to the power k also, so kth moment. So for all j, if it is discrete, and integration from minus infinity to infinity xjk f of x dx for continuous. The next term defined as kth central moment of x. This is given by e of x minus mu times of k. So it can be written as summation x j minus mu times of k. Let's write on the different page. So this is given as e of x minus mu k equal to sum of x minus mu times of k of f of x j if it is discrete, or integration minus infinity to infinity x minus mu to the power of k f of x dx if it is continuous. So this is the kth central moment, and for k equal to 2, the x minus mu square gives the standard you can say variance or square of standard deviation, which is mu square. We'll see that. Now for x and y being random variables, which is discrete or continuous or maybe independent or dependent, in all such cases e of x plus y can be given as e of x plus e of y, and of course it can be extended to any number. Also for x and y being independent random variables, e of xy is given as e of x into e of y. We'll see some more results, but let's move to variance. Basically, variance is a parameter which gives you a measure of the spread of the possible values of random variable. So it's a parameter which gives a measure of spread of possible values of the random variable, denoted by variance x or sigma square. This variance x is actually kth second moment of the second central moment, which we have seen right before, and this will give you the variance. So this is x minus mu square. If you expand, this can be written as x square plus mu square minus 2 mu x. So right now we have seen e of x plus y can be given as e of x plus e of y. We can split this. So this becomes e of x square plus e of mu square minus, we can take this scalar outside of course, but let's take it inside only right now, 2 mu x. Now we have seen the property of expected value that the constant can be taken outside. Now what is this mu? This mu is the mean value, which is a constant now. So this makes it e of x square plus mu square. This 2 and mu are both constant, 2 mu e of x. And what is e of x? E of x is nothing but mu. So this is also mu. So this becomes minus 2 mu square. So the variance x becomes e of x square plus mu square minus 2 mu square, which is e of x square minus mu square, which can also be written as e of x square minus e of x square, because e of x is equal to mu. So this is the sigma square, and sigma is also known as standard deviation, right? Now, right, like we have seen it for the transformation for the case of variance, we can also see the transformation for transformation in the case of variance. If for x we have this variance to be sigma square, then the transformation a times of x will give a square times of sigma square, and ax plus b transformation will still give the variance as a square times of sigma square. So this constant, adding a constant to the variable doesn't change the variance, but scaling the variable changes the variance by an order of 2, a square. Now this variance cannot have a negative value. Variance is always positive. Also, Zero variance indicates that all the values in the sense all the values of x are equal in distribution. Variance of x plus y does not behave like the expected value. So this is variance of x plus variance of y plus 2 covariance of x comma y. This covariance is given by e of xy minus e of x e of y, and if x and y are independent random variable, then covariance of xy is 0 and covariance of and then variance of x y becomes variance of x plus variance of y. Also, a high value of variance results when the values of x is spread a long way from the mean, and a low variance results when values of x are clustered around the mean. That is, let's say this is the random variable and let's say this is the mean, x is equal to mu. So if the graph of this density function is spread, let's say it is spread like this, then in this case we can see that this random variable is spread a long way from the mean value. If this is the mean value, x is equal to me. So in this case you can have high variance. But if the major values, let's say this is the x equal to 0 and this is the mean x equal to mu, then if the graph is something like this, you can see the major values of x are clustered around the mean value x equal to mu. So in this case the variability is less and it has low variance. For the case if it is having low variance, we say it to be having more consistency. High variance is less consistency and low variance is high consistency.